In my previous video on squeeze theorem, I tried to explain the squeeze theorem by the help of practical examples, and I also proved certain standard limits by the help of squeeze theorem. In this video, I'll solve these typical problems by the help of squeeze theorem. Now let's start with the first problem. In this problem, we have to find the limit of factorial n divided by n to the power of n when n approaches to infinity. This limit is clearly infinity by infinity type. So many students would try the L'Hopital's rule. But it will be difficult to differentiate factorial n, and there is a better solution. What we do? We just break the numerator, that is factorial n, as n times n minus 1 times n minus 2 times n minus 3 dot 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 up to n terms, that is up to 3 dot 2 dot 1. We also break up the denominator as n times n times n times up to n terms like this. Now we see that both the numerator and the denominator is the product of n terms. In the next step, we just express the expression as product of n number of fractions like this. Now since n is a positive integer, as because factorial of numbers other than positive integers is unknown, each and every fraction is greater than 0. Even the last fraction 1 by n approaches 0 from the right hand side. So this expression is greater or equal to 0. Again, look carefully that the first fractional term is equal to n by n, that is equal to 1. And the last fraction is 1 by n, whose limit is equal to 0 as n approaches infinity. It can be said that the value of the fractions decrease as we advance to the right. Now let us analyze the fractional term at the halfway mark. The fractional term in the middle would be n by 2 divided by n, which is equal to half. In this manner, we may conclude that the first n by 2 fractions have value less equal to 1 but greater than half, and the last n by 2 fractions have value less equal to half but greater than 0. So this expression over here is less equal to limit of 1 to the power of n by 2 times half to the power of n by 2 when n approaches infinity. Now the limit of both these functions is equal to 0 as n approaches infinity. So we can apply the squeeze theorem and conclude that the value of this limit is equal to 0. Now coming to the second problem. We have to find the limit of the sum of this infinite series. We are actually not familiar with this type of series. Whenever we get this type of series, we will have to find a way to express the series in the form of difference of two consecutive terms, like say root over k plus 1 minus root over k, or say root over k minus root over k minus 1. If we can do this, then the sum of the series can easily be calculated. Now let's see what we can do. First, bring out the constant term root n outside the summation symbol. Then we may write 2 by root k plus root k in place of 1 by root k. Now we bring this 2 out of this summation symbol. Now concentrate on this infinite series. To apply squeeze theorem, we can make this expression a little bigger by reducing the denominator. We make it 1 by root k plus root k minus 1. By this way, the denominator is reduced a bit, and this expression is surely greater or equal to this expression when k is infinitely big. Likewise, we may make the expression a bit smaller also, just by increasing the denominator by making it 1 by root k plus 1. So this expression becomes less equal to this expression when k is infinitely big. Next, we rationalize the denominators of these two expressions like this. The sum of these two series can now be evaluated easily. This one is root 1 minus root 0 plus root 2 minus root 1 plus root 3 minus root 2, and carries on like this till the last term, which is root n minus root n minus 1. Here, the first term of each pair cancels out with the second term of the next pair. Only the second term of the first pair, which is nothing but 0, and the first term of the last pair, that is root n, does not cancel out. So the sum of the series is root n. The sum of this series is root 2 minus root 1 plus root 3 minus root 2 and so on, the last term being root n plus 1 minus root n. Here also the first term of each pair cancels out with the second term of the next pair. Only the second term of the first pair, which is nothing but 1, and the first term of the last pair, that is root n plus 1, does not cancel out. So the sum of the series is root n plus 1 minus 1. Now this thing and this expression over here are the same. Now we simplify and get this without any further trouble. We get limit of 2 when n approaches infinity is greater or equal to limit of sum of this series as n approaches infinity is greater or equal to limit of 2 times root over 1 plus 1 by n minus root over 1 by n. Now, because the value of these two limits is the same and equal to 2, therefore we may apply the squeeze theorem to get the answer, which is 2.